Hello everyone. So in this video I'm going to talk about trees and the relationship between the number of vertices and the number of edges in trees. So first let's give a definition. A tree is a graph, is a connected graph without cycles. So a tree is a connected is a connected graph without cycles. So now in a graph we denote by by V we denote by capital V we denote the set of vertices, and by capital E we denote the set of edges. So this is the vertices, and this is edges. And by this we denote the number of vertices and the number of edges. So we have a theorem that says that in a tree the number of vertices is equal to the number of edges plus 1. So that's the statement that we are going to prove. So we are going to prove it by induction. Induction by let's say by the number of vertices. So first the base case. So when we have a when we have the number of vertices is equal to 1, so basically when we have a single vertex in a graph, then there is no room for any edges, so the number of edges must be 0, so this equality holds. So the base case holds. So now let's assume that the statement is true for n vertices, and we are going to prove it for n plus 1 vertices. So let's consider a tree with n plus 1 vertices. So let's say it looks something like that. That's a tree. So we notice that we always can choose a vertex that has degree 1. and it's called leaf. So vertices of degree 1, all these vertices, they are called leaves of 3. So why is that? So let's suppose that this is not true. So okay, so let's write this. So degree of vertex V is equal to 1. This then V is called a leaf. This is a definition. So we claim, so this could be, we can write it as a lemma. So lemma that any tree has a leaf. Any tree has a leaf. So why is that? So let's suppose that this is not true. So we're going to prove it by contradiction. So suppose not true. So it means that there are no leaves. So no leaves. So the degree of any vertex is at least 2. So for any vertex V, the degree of V is at least 2. So okay, so let's consider, so we start with any vertex, like choose any arbitrary vertex B. So it has degree at least 2, but at least it has an edge that is incident to it. So we go by this edge to some other vertex. Okay, let's denote the first vertex V1. This denote by V2. So V2 has degree 2, so it means that except this edge that we already considered, it has at least other edge, at least one other edge incident to it. We go along this edge to some vertex V3. And so on. We can continue this process. Whenever we come to some vertex, we can always go to the next vertex, because the degree of every vertex is at least 2. So we would never be in the situation where there is nowhere to go. So, but we cannot continue this process forever because there are finite number of vertices in the graph. So therefore, sooner or later, but in a finite number of steps, we would arrive at a vertex that we already visited before. So let's say that vertex Vi is the vertex that we already visited on some previous step. This means that, okay, so let's, just for convenience, so let's denote this vertex Vi. So, and after we traveled along this graph, we arrived at the vertex where we already have been before. So then we see that this And let's say that this is the first time. So let's say vi is the first vertex that where we arrived that we already visited the first time that it happened. Therefore, this path from vi to the next one, so along this path would be a cycle. So this is a cycle. Which is a contradiction because tree doesn't have any cycles. So this proves the lemma. Okay, so there is at least one leaf. So in a tree there is at least one leaf. So if you go back to this picture, so there is at least one leaf. So let's pick this this leaf. It has degree 1. What we can do is we remove. So we remove this leaf. Remove a leaf from the graph and consider the rest of the tree. So obviously this new graph without this vertex, with the removed vertex, it would still be a tree. So this would still be a tree. Still a tree. Because it is still connected. The removal of we removed a vertex and an edge, of course, that is connected to this vertex, but we could not like if any two vertices were connected by a path inside, like this path could not be interrupted by the removal of this vertex and an edge, because it connects only the removed vertex with something else. It doesn't connect anything else. So yeah, so it's still connected, and it still doesn't have any cycles, because if there is a cycle somewhere here inside, it would be a cycle in the original graph with this vertex that we removed. So it is still a tree. Therefore, we can apply the induction hypothesis to it. So it has one. It has its number of vertices is one less than the number of vertices in the original graph. So if we have n plus 1 in this whole graph, if there are n plus 1 vertices, then in the graph is the removed vertex, then there are n vertices, and therefore, okay, so let's remove the lemma. Okay, so let's denote the the original graph T. It had T has n plus 1 vertices. The graph is the removed vertex and edge. It's also a tree. It has n vertices. And its number of edges, so the number of edges E of T prime by the inductive hypothesis. So by inductive hypothesis, this is equal to n minus 1 therefore the number of edges in the original tree T is equal to the number of edges in the tree T prime plus 1 is equal to n minus 1 plus 1 is equal to n, which is 1 less than the number of vertices in T. So and this concludes the proof.